Hello everyone, my name is Zoe. Today I'm excited to share our team's work on LMSYS Chatbot Arena Human Preference Prediction Competition on Kaggle. Our team competed against over 1,600 teams and achieved a top 70% ranking. This project was both challenging and insightful, giving us a deep exposure to a natural language processing, transformer models, and the nuances of predicting human preferences in AI systems. Let me start by explaining the challenge we tackle. The goal of this competition was straightforward but complex. Predict which AI chatbot response user will prefer when presented with two options. We worked with approximately 57,000 human judgments collected from the Chatbot Arena platform. Each sample in our dataset consisted of three key components: a user prompt, two different models labeled as Model A and Model B. The outcome we needed to predict had three possibilities. User could either prefer Model A, Model B, or judge the responses as a tie. Our task was to develop a predictive model that estimates the probability distribution across these three preferences outcome. This is more nuanced than simple classification. We needed accurate probability estimates, not just hard predictions. Now let's dive into the data itself. Before building any models, we conducted a thorough exploratory data analysis to understand our dataset. Looking at the structure, we had 8 main columns: the prompt, response A, response B, Model A, Model B, and the winner labels in binary. One interesting finding was the diversity of the dataset. We discovered 64 unique large language models represented across all the comparisons. This included everything from GPT-4 variants to Claude, Gemini, Mistral, and Llama models. In terms of data quality, we performed several integrity checks. We validated that all required columns were present, flagged duplicates for review, and importantly, we normalized the prompts that were originally stored in JSON format into clean text. This pre-processing was crucial for consistent model training. Now, what about the distribution of the outcome? One of the first things we examined was the preferences were distributed across three outcomes. As you can see from the chart, we found a relatively balanced distribution. Model A won 34.9% of the time, Model B won 34.2% of the time, and ties accounted for 30.9% of the judgments. This is a near equal split across all three categories. It's actually quite revealing to us. It indicates genuine ambiguity in human preferences. There isn't a systematic bias where one position always wins. This balance also tells us that the task is actually quite difficult. Responses are often close in quality, making this a challenging prediction problem. From a modeling perspective, this distribution is actually quite advantageous. We didn't need to worry too much about severe class imbalance, though we still need to be careful with the slightly underrepresented Thai class. Let's look deeper into the model performance patterns. This heat map shows a model performance correlation across three tiers. Top performance GPT-4 variants show darker and red correlations with highest win rate. Mid-range models, Claude 2 and Gemini Pro, perform solidly. Smaller models like Mistral 7B, Llama 2 lag behind. Correlation patterns actually reveal key insights. Positive correlations indicate similar strength. Negative correlation shows different specialization. Model identity signals responses quality, a pattern we captured in our approach. One particularly important pattern we discovered was length bias. This slide reveals a critical finding. Length bias is in human preferences. The graph shows win probability for Model A increases monotonically with length differences, a correlation of 0.2. Longer answers are consistently judged as more comprehensive and useful, with no clear saturation point. However, we deliberately excluded length as an explicit feature. Why? To avoid shortcut learning. We didn't want the model to simply predict longer equals to better without understanding the content quality. Instead, length effects are learned implicitly through token sequences. The model sees actual responses length, but lacks direct access to the length feature that might dominate these decisions. This ensures focus on content quality, not surface statistics. With these insights, we move into the data pre-processing portion. Our pre-processing pipeline consists of 4 critical stages, each addressing specific challenges. Stage 1, data loading and validation. We began by validating dataset integrity, ensuring all essential columns were presented and formally formatted. And a key step was merging the binary winner labels into a single 3-class target variable, consolidated winner Model A, winner Model B, and winner tie into one unified label. Here, we normalize prompts to ensure consistency and work to balance the class distribution across outcomes, paying special attention to the slightly underrepresented Thai class. Next, this is when things get more sophisticated. We use Nivedha v3 as our base tokenizer, but we added custom tokens, user, Model A, and Model B. These special tokens provide a clear structural markers that help model understand the different labels for each sample. Finally, we use the FIFO stratified cross-validation to maintain class balance across all 4 critically. We ensure no data leakage during augmentation by keeping the augmented sample separated from validation sets. Let me explain our representation strategy in more detail. Our facial design strategy focuses on 3 key elements that prove critical to our model success. We serialize our input using explicit role tags. Each sample was structured as user, followed by the prompt, Model A followed by response A, and Model B followed by response B. This tag serves as a stable positional anchors for the model's attention mechanism. Rather than relying on the position alone, the model can explicitly identify which tags belong to which role. This is particularly important for transformer models that need to understand the comparison structure. Given the 512 token limit of our model, we couldn't include every long response in full. Rather than truncating from the tail, we use a proportional head-tail truncation with 70-30 ratio. Why do we use this approach? We preserve both the opening intent when user usually state their questions clearly and the closing justification when user often provide summaries of all conclusion. The middle content, while valuable, was less critical to capturing overall quality signal. Finally, we implemented the order swap augmentation. For each original sample, we created an augmented version where model A and model B positions were swapped, with labels remapped accordingly. These techniques help mitigate positional bias, the tendency for models to favor response in certain positions, and teaches the model to make order invariant judgments. If response A is better than response B, it should remain better regardless of which position it occupies. Now that we cover data preparation, I'll pass on to Krista to move on to methodology.
Thank you, Zui. Now let me walk you through our methodology use. For cross-validation, we used our 5-4 stratified cross-validation, but with one crucial detail. We validate exclusively on the original, non-augmented rows. Even though we trained on both original and swap pairs, we never validated on swap data. This prevented data leakage and gave us reliable, unbiased performance estimates. For our model, we use D beta V3 base with a three-way classification head, optimized with ADAM-W, trained with FP16 mixed precision, gradient checkpointing, and early stopping. Most of our improvement came from a three-stage calibration stack applied strictly to out-of-fold predictions. We applied per-fold temperature scaling, power sharpening, and multi-normal logistic regression, all trained on out-of-fold log probabilities. This calibration stack, trained exclusively on held-out prediction, dramatically improved our probability estimates without requiring us to retrain the base model. Now let's look at how our improvements impacted the performance. Our baseline used head-only truncation, no calibration, and inconsistent validation. It achieved a public leaderboard score of 1.05217. Our final system added with head-tail 70-30 truncation, full calibration stack as main performance driver, and validation on original rows only. This reduced log loss to 1.02744, a 2.35% improvement, and we achieved this without increasing the model capacity. We used the same D beta V3 based architecture for both. The improvement came entirely from better engineering and calibration. We performed application studies to test each improvement individually. Temperature scaling helped to correct overconfidence and improve calibration. Head-tail truncation worked better than symbol truncation by retaining critical start-end context. For order swap augmentation, we moved positional bias to ensure the model judged the content, not the order. And multi-normal logistic regression helped to reduce tie misclassifications. Each of them provided incremental gains, and together they produced a significant overall improvement. We also attempted LLM-based data distillation to expand training pairs. However, this wasn't the performance. It was because the teacher's generic rubric were not aligned with Arena's judging style, and generated responses lacked diversity. This taught us that synthetic data must be tightly curated. It also showed that naive LLM distillation can degrade performance, and that future approaches need better aligned judges and stricter data curation. And through detailed error inspection, we found some recurring issues. The model struggled most with near ties and missing context beyond 512 tokens. Stylistic bias and messy prompts also led to unreliable predictions. By understanding these failures, help us to refine our approach and informed our future directions for addressing these limitations. Looking forward, we identified few promising directions. Extended context modeling using broad scale, D beta or long former models to reduce truncation loss. Class conditional calibration using per class temperature scaling could address the asymmetric miscalibration patterns which we observed across A, B, and tie predictions. Pairwise contrastive training with direct reference head and machine-aware objectives could better capture the comparative learning. Each of these directions addresses specific limitations we observed, providing a clear roadmap for improving our current results. To wrap up, here are the 6 key lessons from our project. First, calibration matters more than model size. Our 2.35% improvement came entirely from smarter training. Secondly, validation hygiene is essential, as leak-free false made our matrix trustworthy. Thirdly, temperature scaling gave us a modest gain. Power sharpening added another, and multi-normal LR contributed further. Individually, each improvement was more, but their composition produced substantial cumulative benefit. Fourth, representation matters. Our head-tail truncation reserve critical context. And fifth, reproducibility requires discipline. This shows when we locked dependencies and ran inference offline for consistent results. And finally, synthetic data isn't automatically good data. Misaligned LLM charges can actually make performance worse. In conclusion, in competitions that value probability quality, how you train matters more than what you train. By improving calibration, data hygiene, and representation, we achieved real gains with the same architecture. Thank you.